Hey grade 5. Today we're talking about fractions, specifically equivalent fractions. This is the reason you should never trust someone when they say they only had one slice of pizza. Depending on the denominator of the fraction, that could mean a whole lot of different things. Let's talk about that. Today, I've made pizza for lunch. Let's cut over to it so I can show you. Now this is exciting to me because pizza is my absolute favorite junk food. I always have room for pizza. Now I've cut it so my partner and I can both have a piece. We want a light lunch, so we're both going to eat just one piece of pizza. Here's how I cut it. You can probably tell what's wrong with this right away. What's catching us here is that the numerator on our fractions of pizza is the same, 1, but the denominator is different. Now there's actually a way to make sure that we're getting the same amount of pizza, but it means that we need to keep our numerators and denominators in step with one another. Let's take it back to the kitchen. Now this plate has one piece of pizza on it. When I cut that piece, however, I was only cutting the pizza in half. That means that this piece is 1/2 of the pizza. For the other plate, I kept cutting my pizza. First, I cut this half in half. Now I have 2/4 of a pizza, but you can see that's still half a pizza. So half my pizza and 2/4 of my pizza are the same amount. Then I cut those quarters in half again. I now have slices that are 1/8 of a pizza. 2/8 of this pizza is the same as 1/4 of this pizza. That means my half turned into 2/4, which could then turn into 4/8. All three of these fractions are the exact same amount of pizza. All of these different fractions equal one another, so we call them equivalent fractions. Now looking at my pizza example, we can tell that fractions can be equal to one another, like 1/2 equals 2/4 equals 4/8. But how can we know which are which? Luckily, it all comes down to simple multiplication and division. Let's take our example from before to demonstrate. Where is my notebook file? Oh, okay, here we go. I've lined up all three fractions we looked at before. Maybe you've already noticed something about them. As we go from left to right, the numerator and denominator keep doubling. First, the 1 becomes a 2, and then the 2 becomes a 4. For the numerators. For the denominators, the 2 becomes a 4, and then the 4 becomes an 8. If we keep this pattern up, you may guess that the next one we could get to would be double 4, 8, double 8, 16. And that's correct. 8/16 is also 4/8, or 2/4, or 1/2. But we've skipped a bunch of equivalent fractions along the way. I've made a second page where you can see the blanks as we go up to 16ths. Let's talk about filling these in. We've got 1, 2, blank, 4, blank, 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 and 8 for our numerators. For our denominators, we have 2, 4, blank, 8, blank, 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 and 16. There's a definite pattern forming here, and it's called multiples. Now, multiples are what you get when you skip count. Every number has multiples, because if we really wanted to, we could skip count by any number. In this case, our numerators are multiples of 1, and our denominators are multiples of 2. But when I skip count by a number, I'm really just listing the different things that I get when I multiply that number by lists. Let's skip count by 7s to show. Well, my first 7 is 7. And then if I'm counting by 7s, I get 7, 14, 21, 28, 35, 42, 49, 56, 63, and our 10th one is 70. That's the first 10 numbers if you skip count by 7s. But if you know your times tables, you might realize this is 7 times 1, 7 times 2, 7 times 3, times 4, times 5, all the way up to 7 times 10. All I've done is list the products of my 7 times table. Now, the fifth multiple is the fifth one in the list, 35, which is multiplied by 5. The fifth multiple of 2 is 2 times 5, 10. So the fifth multiple of 7 is 7 times 5, 35. Going back to our fractions, let's see how this all comes together. Now, we have 1 and 2 as our numerator and denominator, and I can treat both of those as my first multiple in these lists. That means, to get any equivalent fraction, I just need to make sure that I have the same multiple of both numbers. The third one on my list, for example, that I've left blank here, has the third multiple of both numbers. The third multiple of 1 is 3. 1 times 3. The third multiple of 2 is 6, the third number I get when I count by 2's. 2 times 3 is 6. So 3/6 must also be on this list of equivalent fractions. It's equal to all these other ones. We can fill in the others as we go, too. The fifth multiple of 1 is 5. 5 times 1. And the fifth multiple of 2 is 10. 2 times 5 is 10. I apologize for my cat. The sixth is 6 and 12. 6 times 1 and 6 times 2. The seventh is 7 and 14. 7 times 1 and 7 times 2. These are all of our equivalent fractions, all of the different ways that we can say 1/2 up to a denominator of 16. All 8 of these fractions equal one another. Now practically, this means that as long as we're multiplying, or dividing because this works backwards too, our numerator and denominator by the same number, we should be able to find an equivalent fraction. Let's try it with 2/5. Now, if I want to make a fraction that's equivalent to 2/5, I just need to make sure that I'm multiplying both 2 and 5 by the same thing. Let's try and find the sixth multiple of both. To get the sixth fraction from our big list of equivalents if I was to go and list every single one. The sixth multiple of 2, 2 times 6, is 12. So I know my numerator is going to be 12. The sixth multiple of 5, 5 times 6, is 30. So I know, just from knowing my list of multiples up to 10, that the sixth equivalent fraction to 2/5 would be 12/30. The 30 will replace my 5, the 12 will replace my 2. If I find the sixth multiple of both and use those, I can see 12/30 is equal to 2/5. Now let's take one last example and show that it also works the other way. How about 7/21? Now, in this case, what I want to do is called reducing a fraction. That's what we call it when we divide both numbers by the same thing to get a simpler looking fraction. Here, I chose 7 as my numerator because it's what's called a prime number. It can only be divided by 1 in itself. Now, if I divide both of these numbers by 1, I'm just going to get 7/21 again. There's no point in doing that, so let's try the other number, 7. What happens if I divide both of these numbers by 7? Well, 7 divided by 7 is just 1. Any number divided by itself is 1. 21 divided by 7 is 3. So, now I get 7/21 equals 1/3. My 7 turns into 1, my 21 turns into 3, because I've divided them by the same number I've divided both by 7. This means 7/21 can be reduced to 1/3. And that's equivalent fractions. Now one last thing. Though you can always make an equivalent fraction that uses higher numbers, because there's always going to be another multiple. You can multiply by higher and higher numbers. You will eventually reach a point where you can't divide any more. The numbers just won't get any smaller. We call this the simplified or reduced version of the fraction. Usually, if we can use the simplified version, we want to. It just sounds a lot nicer to say I'm done 2/3 of my homework than to say I'm done 16/24 of my homework. As you get further and further along in your math careers, reducing fractions will start to be expected of you. But when we're just starting out, we're happy as long as the fraction you're using is correct. When you're reducing, it's not as simple as counting by that number because you need to understand what you can divide these things by. It really does help to have a good knowledge of your times tables for that. You can guess and check, but it'll take you quite a while. Good luck, everyone. Peace.